which is minus RT over L. So help me take the derivative of this, because this isn't right. This term isn't right. What's the derivative of I naught e to the minus RT over L? When you take the derivative of an exponential, what do you get? You get the exponential back.
Right.
What do you do with the stuff in the exponent?
Comes out in front, doesn't it?
Yeah,
Oh, yeah.
you basically take the derivative, there's a t term, so you get that stuff out front, so you get the minus r over L out front, and then the exponent back.
Right.
And then this term just goes back out front.
Right.
Okay. So that cancels the L. That's what's happening here. So we have minus I naught R e to the minus, actually this minus, and this minus, and that minus came from the exponential, so this becomes plus e to the minus t over tau sub L. Okay, so this was wrong. So I naught R e to the minus tau over tau sub L. Okay, this makes sense, right? You'll notice it's the same as your resistor voltage. Why does that make sense?
Ohm's law.
What's that?
Ohm's law,
Ohm's law?
right?
Yeah, basically, if you look at the circuit when it's moved, this is the circuit. If you've got a voltage drop across your resistor, then you'd have to have an equal voltage rise across something else so that the net voltage is 0. Actually, that would require there to be a negative, so those voltages are equal and opposite. Once you're going to have a voltage drop across your resistor, you'd have to have a voltage rise across your inductor. So this would have to be minus for that to be true. Sort of like we talked about it in terms of like if you've got water and a waterfall on a pump, if it's going to fall, the water is going to fall off the resistor. The water, goes down like the voltage drop. Then something's got to pump it back up. And so what's pumping it back up would be that inductor. So there would have to be an opposite voltage on the inductor than on the resistor. Maybe it makes more sense to make this positive and this negative. Like we always said when we did
Because it's a
Resistor.
Kirchhoff's
resistor.
law. Yeah,
The
there's a
resistor
negative.
negative.
Yeah, that's probably make more sense. And then I gotta update these slides because that's 2 terms in a row that this was not correct. Okay. All right, that's clear. Okay, so sorry for the mistakes, but were there any questions about how we fixed the mistakes?
Makes sense.
Makes sense once we fixed it. Yeah, it did make sense at first. So, any questions then about falling currents in general? I'm thinking we've got time to do. We've got 10 minutes. We probably could do one of these 2 problems. So let's do problem 3027. I think we can do that in 10 minutes.
With your
Okay,
Yeah.
I could do it all on one
sticky note?
sticky note.
Oh no.
So hopefully that's 10 minutes of work.
Oh,
Per sticky
yes.
note, 10 minutes, okay.
Yeah, and then we'll come back from lunch and do activity 6.6. That's just from our old textbook, because this book doesn't have very good problems, so I picked one from our old textbook.
Why don't we just use the old textbook?
It's a terrible textbook. It's a terrible, terrible textbook filled
But it has
with
good
errors.
problems.
Yeah, I mean, like, there were equations in the book that were wrong, the explanations were horrid, the examples were horrid, or not even there.
But the problems were good.
Sometimes the problems were good. But in this particular case, they had a better problem than our current book has, so.
Okay.
It's hard, you know, when you're reviewing textbooks, there's a whole lot of like, not great, you know. There's very few textbooks that I've read and been like, yeah, this is perfect. They're all kind of like.
Have their yays and nays.
Yeah.
Mhm.
Okay, so problem 3027. So we've got this figure. Everyone have the packet?
Mhm.
Okay, so we see this figure. We've got two switches, so just looking at this figure, if the switch S1 is closed, then you're in what? Rising or falling state?
Rising.
Rising. And then if S2 is closed and S1 is open, then you're in the
Falling.
falling state. Okay. Okay, so we have a battery of 60 volts, a resistor of 240 ohms, and an inductor of 0.16 henries, with switch S2 open and switch S1 closed, until a constant current is established, okay? Then S2 is closed and S1 is opened, taking the battery out of the circuit. Okay, so I'm gonna start and just draw what the effective circuit looks like, so we don't get confused. So, a couple things they said here. They said that first switch S2 is open and S1 is closed until a constant current is established. So what's the important thing we need to take away from that?
It's what reaches.
Constant current.
Constant coming, well, it's gonna build.
So it
It was
builds
just
and builds
increasing.
up
It's
until
increasing.
it got to
Constant.
the max.
Right.
Yeah, so when battery was connected, I of t, I sub L of t reached I max. And what was I max from, what did we learn I max was? Well,
E over R.
yeah, E over R. So that means that our initial current in the falling state is going to equal I max. All right. Now looking at that circuit, what direction across? Oh, they ruined it for us. Look right. All right. So you guys look at the picture. Do you agree with the direction that they drew the current in?
Yes.
They show the direction going to the right across the inductor. No, that's lame. They should ask that question. That's for sure.
You pick.
Okay. So that's the direction of the current. All right. Okay. What is the initial current in the resistor? Oh, so we'd already answered question A. What's the initial current in the resistor just after S2 is closed and S1 is open? Okay, so we answered that question. What would that be then? I naught is, what was the E of the battery?
60.
60 over 240. What is it? A quarter?
Yep.
I think it's like 250 milliamps, yeah.
Yeah, actually 6 over 24 would be
200.
a quarter. 0.25 amps?
Yes.
All right. B, what is the current in the resistor at time equals 4 times 10 to the minus 4 seconds? At time equals 4 times 10 to the minus 4 seconds, find the current in the resistor. Does it matter whether we're talking about the current in the resistor or the current in the inductor? No, and why not, Hannah?
Because it's the same throughout major loop.
Yeah, it's a single loop, the current's the same in all devices. So find I sub R, which equals I sub L. So we got our equation for falling currents over there, and I sub L, the equation is I naught e to the minus t over tau sub L. So we have I naught, that's that 0.25 amps, And then should we calculate tau sub L, so we don't have to plug a bunch more stuff in the exponential? Remind me,
Sure.
what's the equation for tau sub L?
Oh,
So tau equals L over R.
L over R. All right, so what's the value of L they gave us?
0.16 Henry over 240,
Okay,
which gives you 0.000667.
okay. And then what's the units of the inductive time constant?
Seconds.
Seconds. And it better be, because we've got time over time constant, so the units have to cancel, yeah. Okay, so I'll let you guys plug in your numbers, and so you get the practice of plugging in those numbers, and we'll see if you guys get the right answer.
yeah. What difference is- Okay, makes sense.
What'd you guys get? Everybody done?
137
0.11.
million.
2.
So one person got 137 milliamps
So
and,
I got, that's what I got.
0.137.
okay, so a lot of people got that.
We did the other one right there, the one right there. Did you know what I, oh, this is reference to class.
So that is
M2U,
correct, so if you didn't get that, maybe consult a neighbor, make sure
So-
you typed in everything the same.
Okay. Nothing's just- Let me see.
I'm lost.
I know. Let me try that. Got that, I'm not sure.
Here, I'll show you if you're lost about what we're plugging in. So I naught we calculated was 0.25 amps, and then E to the minus T, they said at time equals 4 to the minus 4 seconds, so that's our,
There's where the T is.
Little t.
Okay, that's what I did.
and then tau we calculated was that 0.000667 seconds.
Second T.
So all that needs to be in parentheses.
Yeah. I already messed it up.
Yeah, Jacob?
It's kind of handy to calculate 1 over tau, which
Uh-huh,
it turned out being negative 1500 T. It's the basic
a lot
calculation
easier
we're
to
looking
use.
at.
Okay, I'll put that in a different color so you guys hopefully can see it.
Which is
I'll just put that up
1
here.
over tau. Yeah.
1500.
Yeah.
Okay, so that's true. That's much handier since you're always using 1 over tau in your exponent. Okay. Part C then. What is the potential difference between points B and C at the same time? Which point is at a higher potential? Points B and C in our circuit. Okay, so talk to me logically about about this. So we kind of already worked this out over there when we're solving for the voltage drops. So is current, is the voltage dropping across your inductor, or is it rising across your inductor? Think about the water pump.
Rising.
Yeah, so it's the pump, whereas this is the waterfall. So would point B or point C have a higher voltage?
C.
See?
C, yeah, so this is 0 volts, then this would be the high voltage. And then it's going to drop back to 0 as it goes across the resistor. Okay, so that answers that part about which point is higher. Okay, and then what equation are we gonna use to find the voltage from B to C?
The top one that you,
Yeah, so the one for the inductor, because that's the inductor we're going
Yeah.
across. So same time, 4 times 10 to the minus 4 seconds. V sub L is I naught R e to the minus t over tau sub L.
Yep, that's right. For one. For one, are we doing?
So try plugging in those numbers yourself and we'll see if we all get the same answer.
So since we already solved I naught e to the negative t over tau, can't we
just
just
multiply by
Oh.
yeah.
Good call, good call. So this we calculated, I erased it, but that was 137 milliamps. So you can put in, this would just be R times 0.137 amps,
32.9.
32.9. And what's the units?
It's V, so it's voltage.
All right. Consult my sticky note. That's what I got. Any questions about part C? Okay, the last question is,
What's that?
how long does it take the current to decrease to half its initial value?
That worked much better.
Oh man, I was going to erase this current, but that's what we're asking about, so I'm gonna erase these other equations.
Half of the current?
So, yeah, so to reiterate what they're asking is they want to find the time when the current
Is it its peak or?
equals half
Oh.
its peak value, I naught.
Well,
So what
do
are
we
you
know what the
going
peak
to-
is already?
We do know the peak,
Okay.
okay? So how are we gonna find, what equation first, what's the equation we're gonna be using?
equation for falling current?
Okay, the falling current equation. And what are you gonna first do to that equation?
Solve for t.
Solve for time.
Solve for time? And how would you like to do that?
So
Algebra.
T over tau
Yeah.
equals 1/2.
There you
Okay, so first I'm gonna plug in, doing what Hannah says, I wanna show a few steps here. So for I sub L, I'm gonna put in 1/2 I naught equals I naught e to minus t over tau sub L. Since that's that condition we're looking for. So with that, we have I naught on both sides, so that cancels. And then we get where Hannah said we should be, is 1/2 equals e to the minus t over tau sub L. Okay,
Natural log.
natural log.
Mm-hmm.
And what happens to the right-hand side when we take the natural log of an exponent?
E dies a horrible death.
I love that. All right, so we just get the exponent back. And so tell me, what does t equal then?
Negative natural log of 1/2 over tau.
Actually, tau would be,
TL times ln.
yeah, multiplied on top.
That's the negative, isn't it? We're gonna switch it. Oh, okay, got it.
Okay,
Right.
so this should be solvable now. And I just wrote on my notes that I think this makes a great test question.
We're going natural laws, exponentials, and yeah, right up what I remembered.
Well, you see
Deep
it.
in, I have,
Now
it's
you
just been in the back of my head.
Oh, yeah. It always has to come back to the forefront in the
Yeah.
cobwebs.
It's like, wait a minute, natural logs falling in there somewhere.
Exactly. So anybody get an answer? What did you get, Derek?
4.62 times 10 to the negative 4 seconds.
Anybody concur?
Yes.
Yes, concur. Okay, great. And so is this, let's see, where is that compared to what we found before? That time equals 4, so it's a little bit after the other point in time we were looking at.
Which makes sense.
Yeah. So, how do you guys feel about this problem? All right? I think it would make a good test question.
Because?
Because it asks you, it asks you a variety of things relating to the RLC, or the RL circuit.
Because it has more than one equation is what you're saying. It's
Yeah,
got
it
some
forces
stuff
you
gotta
to
fix.
know a variety of different things. There aren't any tricks. You can use logic to answer some parts of the questions. And time-wise, it fits in sort of with a typical test question for the length and how long it would take to solve. That's my thinking. So,
Yeah, I like that, it's straightforward.
yeah, it's straightforward. That's, another thing I look for. Nothing you're gonna look at it and be like, oh. None of like, fall for the rate of change of energy transfer to mechanical energy from something else.
Finding a bunch of words and throwing them in there.
Right. Okay, let's take a break for lunch. What time is it? It's